And welcome back to Electronics Experimenters Kit, Experiment 16, a current mirror source, using PNP transistors and the problems involved in this circuit. So sit back and enjoy the show. This video is sponsored by PCBWay. Whether it's standard PCBs you want, or advanced PCBs, or for that small, confined and well packed piece of kit, a flexi rigid to save on the wiring and the PCBs. They'll also do assembly, and if you don't want to do the assembly yourself, then you can order a stencil to do the surface mount yourself. And of course, once you got your board finished, you might want a box to put it in. And so they do CNC machining, sheet metal fabrication, 3D printing, or if you're going to sell a few, you might want to look at the injection moulding and vacuum casting. So the next time you're doing something, don't forget, pop over to PCBWay and see what they can do for you. Right, so I just thought I'd do a recap about the current mirror. So this is the current mirror, and what do we know about it? Well, we know that Q1VC is the same as Q1VB, as they are shorted together. There's a diode junction between the emitter and the base of Q1. That diode junction can have a voltage of around 0.6 volt, depending on the current. The lower the current, I suppose, the lower the voltage might be. In this case, the circuit VCC is 15 volts. So if you want to know the voltage on the collector, then it's here, VCC minus Q1's VBE voltage, which is we're taking as about 0.6, and therefore the voltage on the collector is 15 volts minus 0.6 equals 14.4 volts. That leaves us in then what is the current flowing down here? Well, it's flowing down here for a 10k. So we have a collective resistor of about 10k, and the current flowing through Q1 is approximately 14.4 volts divided by 10k at 1.44 milliamps. Now, as you can see, this is dependent on current flowing. It's a diode. The more current that flows, the greater the volt drop will be. And so if these two transistors have exactly the same characteristics, and that's quite important, they have to be the same characteristics, then whatever voltage across here with that current flowing down here is exactly the same as the voltage of the base emitter of this transistor. So if the characteristics are identical, the current flowing down here should be exactly the same as the current flowing down here. And that's how the current mirror works. There are issues if you use two separate transistors, then you can't guarantee the characteristics are the same. You can't guarantee that the temperature in the transistors is the same. Most of the characteristics of a transistor are temperature dependent, and so warm up one and cool the other, or the other way around, and they will go out of balance. So let's put the circuit together and see how we get on. Right, here we have the first circuit, and the wiring for this will be shown up there. Well, an enlarged picture of that will be shown up there, and the circuit of that little bit there will be shown down there. Right, just to show you, we're going to be running this off a single rail, 15 volts. So we'll stick that in there. We have 15 volts here. We have a 10k resistor there. So if we move this down to there, let's plug it in. We have 14.37, and that is one diode drop down through there, because if you look at the circuit down here, you'll see that the transistor on this side, the base and the collector are shorted together. So we have one diode drop, which is the emitter to base diode. That is flowing through the 10k resistor. So effectively we can move the the 0 to there, or the dot to there, and it will have 1.4 milliamps. And we can check that by, I've got the current meter coming in on this wire, and if I pull the green one out, you will see up here that the current is now 1.43 volts, 10k, so close enough. So if we plug the ground back in, pull the current meter out, move the current meter over here to the output side, pull the ground out. On what? We've got 8.3 milliamps flowing down here. And this is meant to be a current mirror. This side is meant to be mirroring that side. And this is using a dual transistor. And this is a typical setup as shown in the art of electronics. You know, the programming current, or the current you want your mirror flowing down here, is the voltage here, VCC, minus VBE, one diode junction, divided by the resistor here. And as you've seen, we had 15 minus about 0.66 or 68, or no, 62 in it, giving us 14.38 across 10k. This current is not working. And so what I'm going to do now is I'm going to change that, and I'm going to put a circuit of a individual transistor. So I'm going to put 2 transistors in here as shown down there, and again it'll blow up the board up here, and we'll see what happens. Let's just turn the power off while I pull this one out, find the right one. Right, it's this one keeps popping off, so I'll put that back in. We'll move current meter back to the programming current side. We'll put power back on. You see 14.36, we had about 14.38 before, didn't we? So yeah, we've still got about 1 diode drop. If I take the ground out, you see we've got roughly exactly the same current, 1.43 milliamps flowing down there. If I put the ground back in and we move the current meter over to here, pull the ground out, as you can see now, it would appear that these 2 individual transistors shown up here are better matched than the 2 that are on the same piece of silicon. The only problem now is if I put my finger on one of these, you'll see the current changing, because I am warming up one transistor and not the other. So the characteristics of one is changing because of the temperature and the other one's not. And the whole point of putting a dual transistor in is that the 2 transistors should be on the same die, and they should be virtually identical. The characteristics should be almost the same because they're made at the same time. That's the theory anyway. Maybe the ones I'm using aren't that well matched. So what I'll do now is I'm going to put in another one, only this time we're going to use something that's referred to as emitter degeneration. Well, before we move on, we're going to have a quick look at what emitter degeneration does. Emitter degeneration is basically those 2 resistors. So I've got a new circuit. So what do we know about it? Well, again, Q5 collector and base are shorted together, which they are. There's a diode junction, which there is. A diode would have about 0.6 of a volt at low current. Yeah, we know that. VCC, again, it's going to be 15 volts, but I haven't put 15 volts up there. And these emitter resistors are going to be the same value, or as close as they can be. Right, so let's have a look at the current flowing in Q5. Let's see, it's quite the same as before, only we've got this extra resistor. So it's basically VCC minus VBE divided by the value of R7 and R13, with R7 being 100 ohms, and we've still got the 10k for R13. And then, so quite effectively, or approximately, the current in Q5 collector is 15 minus 1.6, which is 14.4, divided by 1100 ohms, which comes out about 1.31 milliamps. And we know that the voltage across here is dependent upon the current flowing down here. And we know that if the characteristics are the same, which we know they're not, then current down here should be the same. But if we look at a graph of the base emitter voltage as a function of the collector current, which will appear magically up here somewhere, it shows that there's quite a current change for a slight base voltage change. And so we get a kind of negative feedback by adding this resistor, because we know that a certain VBE here gives us a certain current, and we got the same VBE here, but we've also got a slight voltage drop across here. Now, if this slight VBE voltage gives a higher current, then a higher current is going to flow through the 100 ohm resistor. This higher current means there's going to be a higher volt drop on this resistor than there is on this resistor, and so effectively the base voltage is going to reduce because this voltage is going to shift and this voltage is not. So that's effectively going to reduce the base voltage, which will reduce the current. And so it's a kind of negative feedback, and that allows the characteristics of the transistor to spread a bit, and it will bring the current down here closer to the current flowing down here, which you'll see when we breadboard it. I'm not going to go much further than that, because if you want to go more further than that, there's more maths. And I hate maths. So back on with looking at the examples. And so what that basically means is you'll see in the circuit down here, that's going to be there, that there is in fact two resistors, one in each emitter, and they are going to drop a slight voltage across them, and that is going to impart some negative feedback onto the transistors, and that is going to help broaden out the characteristics of the two transistors, and that should give us a better mirror. So what I'll do now is, again, I'll turn the power off and I'll stick with the two transistors, the two separate ones, and we'll put one in, and I'm going to put my degeneration resistors are going to be 100 ohms, and that will give me, I won't lose so much. I'll only be having about 1.14 of a volt drop across them, because if you put larger values in, you'll get a higher volt drop. It will work slightly better, but you're losing the headroom. You know, whatever you put in the emitter has a volt drop across it. If the transistor is fully saturated, it will be about 0.6, 0.8 of a volt, and so that is the closest you will get to VCC when it has to get hard on to the top. Right, let's turn the power off. Pull that one out. Find the one that's got the 100 ohm resistors on. What I will do is, I think at some point, is I shall get PCBWay to who are sponsoring this video to make me some new boards so that we can do this. Right, that one's back in, power back on, and as you can see now we have 1.53 milliamps flowing down there, which was better than the 2 point something we had before. If I put the ground back in, move the ground over, pull the ground out, and here you can see we've still got about 1.42 milliamps flowing down there. Oh, that leads alive. So we're getting better, you know, instead of being twice as much or nearly 7 or 8 times as much, we're now down to a few hundred microamps difference. And so the last one I'm going to do is I'm going to replace that with dual transistor again with the same thing. It's going to have 100 ohm resistors in the emitter line. So let's turn the power off, pull this one out, pull this one in, power back on. Right, as again we have still got the 1.42 milliamps flowing down here, hence the 14.23 volts across. Again, it's the emitter base resist diode that is dropping the 0.6 or so from the VCC to the point we're measuring. And if I move the current meter to this side, oh, I shouldn't have done that. I should have put that one back in first. Move it over here, and as you can see, the dual transistor is now behaving itself. The degeneration resistors in the emitter are helping. They're making that a much closer current mirror than it was. It was wildly out before, wasn't it? Now it's close. Well, I hope you like that, and I'll catch you on the next episode of the Electronic Experimenters Kit. Bye for now.